Video number 5, pre-calc, section 1.4, lesson 5. Checking out number 85. The recommended distance here, D, that a ladder should be placed away from a vertical wall is 25% of its length. So ladder length, height of the ladder off the wall, and then the distance between the base of the ladder and the home. Approximate the height that can be reached relating H as a percentage of L. So here's what I was thinking when I worked this out. The distance D is 25% of its length. So you can write an equation right away with that. D equals 0.25 L. That's what it means for the distance to equal 25% of the ladder's length. Now, what's the other thing we have to work with? Well, the other thing we have to work with is the fact that we've got a right triangle relating the D to the H. They meet at basically a perpendicular angle there. So what we can do is use the Pythagorean theorem to say D squared plus H squared equals L squared. All right. The reason why that is helpful is because we need to approximate the height as a percentage of L. So you can replace the D with the 0.25 L. All right, taking that and we're plugging it in for D. At which point, and again, 0.25 is the same as 1/4. I work a lot better in terms of fraction squared than decimal squared. So 1/4 times 1/4 is 1/16. L times L is L squared. Plus H squared is equal to L squared. So if I subtract 1/16 L squared from both sides, think about the fact that there's a coefficient of 1 in front of that L squared. And I'm really just taking 1 minus 1/16. So H squared is equal to, well, what's 1 minus 1/16? Should be 15 over 16. You can either think of it as a full 16 over 16 minus 1, or if you need to, find the common denominators. 16 over 16 minus 1 over 16 is 15 over 16. We're really tasked with getting H by itself, so we square root both sides. We don't have to worry about a plus or minus because we're not really dealing with a height that could be negative. So root 15 over 16 L squared, root 15 over 16 L squared, you can think of that as, this is L times L. This is root 15 over root 16, which would be root 15 over 4 times L. And yeah, when you actually take root 15 divided by 4, you get 0.968 L. So really, what did we accomplish here? We know that the height is always going to be approximately 96.8% of L. This was 25% of L. This is 98.6. I'm sorry, I keep saying 98, I mean 96. 96.8% of the ladder's length. So, interesting little ladder problem there. Let's move on to number 87. Oh, it's frozen. Let's get it. There we go. All right, so it says power line is going to be installed right here. And then it's going to keep going all the way to the power station. And it's got to go across a river that's a mile wide. So there's 1 mile. This little distance right here is called x. And we know this whole thing is 5. Okay? So I'm just going to call this distance right here, 5 minus x. So we're assuming that there's a 90-degree angle here, which is helpful. And it says that a power line is to be installed across the river that's a mile wide to a town that's 5 miles downstream. It costs $7,500 per mile to lay the cable underwater and $6,000 to do it overland. How much cable should be installed if $35,000 is the project's allocated budget? Well, the first thing I would think about is just doing an equation that basically reflects the cost in every way. Hey there, I'm over here now. So when you think about it, if we gave different variables, like let's say that we'll let this variable y represent the distance underwater, the distance that the cable needs to be underwater. $7,500 times that y value is how much it costs to lay that cable. In terms of miles, that is. If we add to that $6,000 times this distance right here, 5 minus x, we need $35,000 to be the equivalent cost. So, we've got our first equation that relates x and y. So I can do a little math here. I can just say 7,500y plus 30,000 minus 6,000x is equal to 35,000. All right, can you see all that? I believe so. Subtract 30,000 from both sides. And you've got 7,500y minus 6,000x is equal to 5,000. Now this would be super helpful if we had a second equation that gives us a relationship between x and y. So if you see, we got a right triangle here that has sides 1, x, and y. If we use the Pythagorean theorem, we can come up with a second equation that has both x's and y's in it. And then we should be able to solve from there. So our second equation is 1 squared plus x squared equals y squared. So these are the two equations we want to work with. And I'm going to go to this side of the board because it's closer to the camera. Ah, there we go. So when you look at this, the question is, what seems to make the most sense in terms of solving for either x or y? And when I did this the first time, I got one of these by themselves. I said to myself, well, if we just square rooted y squared, then we have y equals a root value. It does create a little bit of, wonky calculations later on. I almost wonder if we should try maybe a different approach, but I'm not exactly sure what if that's going to lead to a quicker method. So I'm just going to go with what I did when I worked it out the first time. Sorry, that was very anticlimactic. So y equals root 1 plus x squared. We're not dealing with the plus or minus because all of this has to be, it's got to be a positive length here, so don't even mess with the minus. That will now go in for the y in this equation. So you should get 7,500 times root 1 plus x squared. We had 7,500y, we have 7,500 now root x, 1 plus x squared. Subtract the 6,000x equals 5,000. To solve an equation with a root, remember we talked about getting the root by itself. So adding 6,000x and then dividing by 7,500. So 5,000 plus 6,000x divided by 7,500 on both sides. So divided by 7,500, divided by 7,500, divided by 7,500. Before I square both sides, just keep in mind that these cancel and you're left with 50 over 75. Well, 50 over 75, if I divide the top by 25 and the bottom by 25, is the same thing as 2/3. And then over here, I'm left with 60 over 75. They both divide 15, so it's 4/5. Yeah. So then if you squared both sides, you're left with a fraction bonanza. 1 plus x squared is equal to... to do a perfect square, a shortcut that you can do is square the first, square the last, 16 over 25, x squared, and then double the first times the second. So the first times the second would be 8 over 15, x, and then you double that. It's 16 over 15x. From there, I ran out of room again, so we'll go to this opposite side once more. Let's get the 1 and the x squared to the other side of the equation. So I'm going to rewrite this. It's going to be 16 over 25 x squared plus 16/15 x plus 4/9. And then I'm going to minus 1 here. Minus 1x squared minus 1x squared. So it's 0 equals, this is like a 1 in front of the x squared. So 16 over 25 minus 1 is like 16 over 25 minus 25 over 25. Still 16 over 15x, and then 4/9 minus 1 is the same as 4/9 minus 9 over 9, negative 5/9. Okay. At this point, I want to put it in the quadratic formula. So you can find the decimals for those to get an approximation. I'm going to plug in negative 9/25 for my A term, 16 over 15 for my B term, and negative 5/9 for my C term. Here are the two answers I get. And sorry, I just skipped the whole step with the quadratic formula, but you guys have seen it before. It's going to be an ugly mess in there. Those are the decimals that come out of it. And what that basically means is this distance right here, our x value, oh no. That's not the question I'm answering. Determine how the cable should be installed if it's basically what you want to do is you want to install Y amount of cable here if X amount of cable is happening over there. So we found these are the two X units that would optimize our, not really optimize, just say like those are what gives us 35,000. So when X, all right, when this distance right here is 0.674 miles, then we get the $35,000 range there. When this distance is 2.289 miles, it gives us the same thing. So just to make sure you guys know how to process this information, the thing we solve for X is this distance right here. If they explicitly asked how much underwater cable should be installed, they just said how should the cable be installed. We would have to go back and plug this in for y equals root 1 plus x squared. So, we can do that right now. If I plug 0.674 in for the x here, you would say we'll go 1.206 underwater miles. And then we would say take 5 minus the 0.674. This is your first option that's related to this solution right here. Your second option would be to plug in 2.289 here, which would mean you do 2.498 miles underwater. And then take 5 minus the 2.289, which would result in 2.711 miles over land. So it's like we got two different scenarios that they can play around with to get the same $35,000 budget. All right, thanks for watching.